This is the autonomous pipeline inspection robot built by Group 17-2-4, Jackie, Jay, Mitch, and Sam, supervised by Dr. Jaho at Ontario Tech, a fully wireless inspection system built to detect pipe defects in real time.
The firmware runs on ROS2 Humble on the Jetson Orin Nano. ROS2 handles all the communication between our sensors, our motors, and our compute hardware. Everything talks to everything else through a standardized topic system, thanks to ROS. During our initial testing, you can see the motors responding to commands sent wirelessly from the operator laptop through the Jetson down to the ESP32 microcontroller, all happening in real time with encoder feedback, confirming the motors are actually doing exactly what they're told. On the mapping side, we used RViz2 to visualize the depth camera output in real time. As the robot moves through the pipe, the RealSense D435i generates a live 3D point cloud of the pipe interior that you can see building up in RViz2 as it goes. The depth camera also feeds into our autonomous driving pipeline, using the live depth data to keep the robot centered and moving straight through the pipe without any manual steering input from the operator.
Some of the design goals for the mechanical platform of our robot was for it to be both low cost and modular for cheap and maintainable autonomous platform. Since our robotic platform needed to withstand corrosive environments, we selected stainless steel and polypropylene as they were resistant to hydrogen sulfide gas, commonly found in sewers, and readily available materials. Additionally, we opted for sheet metal body panels instead of a completely stainless steel body. This would reduce costs of both raw material price and would also reduce manufacturing costs. Meanwhile, the track housing could be 3D printed since polypropylene is 3D print compatible. Alternatively, the housings could be injection molded should there be a need for increased production. In the end, we did finalize a design that is both low cost in comparison to other industry platforms, while maintaining modularity as a quality of life feature for regular maintenance.
The electrical system is the backbone of the robot. Everything runs off the single 14.8-volt LiPo battery, which powers the motors, the Jetson, the depth camera, and the wireless system all at once. We ran it for 86 minutes straight under a full load, which is well past our 55-minute target, and it had no issues. Power is distributed through a centralized system with fuse protection at every level. If something goes wrong, the robot then fails safely. On the software side, the camera feed is live streamed to the operator over Wi-Fi, which means no tether and no cables to mess around with at deployment. The operator opens a browser on any device on the same network and gets a real-time 720p view inside the pipe. Defect alerts appear directly on the screen as they happen, and the whole inspection is monitored remotely, meaning nobody needs to go in or near the pipe.
So here we see a defect being detected by the robot. This pipe inspection robot is currently able to detect two different defect types using its depth camera. The first is ovality defects, which you just saw, and it includes pipe warping or dents. The camera looks at the pipe walls a couple of feet in front of it and fits an ellipse to calculate the ovality score. If the score is outside of a specified range, a defect is flagged. Next, we are going to see it detect a blockage in the pipe. When either defect is detected, it then saves a point cloud map file with the defect. Here's a post-processing viewer. So first is the blockage. Here we can see the blockage without the pipe around it, and then here with the pipe. In the viewer, we can move around and zoom in and out. So similarly, for ovality, we can see the pipe with the exact location of the defect that's marked with a red dot. Thank you for listening to our video.